So let's talk about the isoelectric point, also known as the pi. Lowercase p, capital I. This stands for the isoelectric point, and it is the pH where the Zwitter ion dominates. The pH where the Zwitter ion dominates. That will be our definition of the isoelectric point. So it refers to actually a pH. Now, the Zwitter ion is just the molecule that has a neutral charge. So a net charge of 0, or neutral. Okay, neutral. So the pH where the neutral form of the molecule, whether it's an amino acid, whether it's a peptide, or whether it's a protein with 500 or 600 amino acids, the pH where the 0 net charge of the molecule dominates. You remember, amino acids have pKa's, and due to that, when we join amino acids together to get peptides and eventually increase in complexity to get proteins, they will have different charges on the molecule. Well, the isoelectric point is really where the pH, where that molecule, whether it's a peptide or a protein or even an individual amino acid, it is the pH where the 0 net charge of that specific molecule dominates. So let's take a look at a simple case of an amino acid, realizing that proteins will have a pi, hemoglobin will have a pi. All these proteins and enzymes that you will study in this course will have a pi. Let's just take a look at the amino acid aspartic acid, just as an example. Now, a caveat here, you're going to need to know your pKa values for whatever molecule that you're going to want to calculate the pi of. So use your flashcards. Okay, the pKa's of individual ionizable protons are not something that you memorize. They are something you consult. And in this case, in the first days of the class, I've told you to make flashcards of the amino acids, all 20 amino acids, as well as the pKa's of any side chain ionizable protons, as well as the alpha amino proton, as well as the alpha carboxylic acid proton. So aspartic acid, let's calculate the pi, the isoelectric point of aspartic acid. First of all, let's draw the structure of aspartic acid. Now, when you calculate the pi, you want to start with the protonated form. Okay, completely and totally protonated. Everything has a proton that is attached to it. All right. So start with the protonated form on these pi problems. I've seen students mess up where they start with a form initially where the proton has been off. No, you want to start off where all the protons are on every part of the molecule. So this is the structure of aspartic acid. Just as a reminder, start with the completely protonated form of the molecule of interest, in this case aspartic acid. So start with the completely protonated form of the molecule for pi problems. Or for pi calculation. All right. So here we have aspartic acid. And this is where you're going to want to use your flashcards that you have and use the pKa values that you know. So what are the pKa values for aspartic acid? The pKa value for the alpha amino group of aspartic acid, looking at my notes, I have this at around 9.90. For the alpha carboxylic acid, so that's the alpha amino group, that's pKa of 9.90. The alpha carboxylic acid, that has a pKa of roughly 1.99. Actually, it's an exact value of 1.99. And then, that's not all, because the side chain of aspartic acid also has an ionizable proton. And when I consulted my notes, that one is about 3.90. Okay? So we want to figure out the isoelectric point of aspartic acid. Okay? So first thing you want to do is determine the overall charge that you started out with, completely protonated. And the completely protonated form of aspartic acid has a net charge of +1. Okay? +1. Right? Now we just tick off protons one by one. All right? So here is aspartic acid. Let me zoom out here so that we're going to take up a major portion of the paper. What is the first proton that comes off? Okay, the first proton that comes off will be at pH 1.99. So when you have a pH of 1.99, this proton, the alpha carboxylic acid proton of aspartic acid, begins to come off. And then we have this. So when your pH is exactly 1.99, what does that mean? It means that you have 50% of the molecule in +1, and you have 50% of the molecule in this form, which has a net charge of 0, also known as the Zwitter ion. Okay, so the Zwitter ionic form is the form where you have a net charge of the molecule at 0. So at pH 1.99, you can imagine if we have aspartic acid and we slowly add some base to it. It doesn't matter the concentration. It doesn't matter the conditions of this. But we're going to just add or increase the pH until it's 1.99. Once the pH is exactly at 1.99, we have 50% of the +1 form and 50% at the Zwitter ion neutral form. All right. As the pH increases to pH 2, pH 2.5, pH 3, pH 3.5, what do you imagine would happen to this form, the +1 form, and what would you imagine happen to the Zwitter ionic 0 charge form? Well, you can imagine, well, at 1.99 we're 50% this, 50% that. As we increase the pH and move away from 1.99, we are diminishing this form of aspartic acid and favoring the Zwitter ionic form of aspartic acid, okay? The form that has a charge of 0. Right? So the pH increases, increases, and increases. We have more of this, less than that, until we hit a pH of, can you guess? pH of 3.90. When we reach a pH of 3.90, this proton begins to come off. And that is going to have this structure. What is the net charge of this form? The net charge of this form is -1 when we begin to hit a pH of 3.90. So what happens when the pH is exactly at 3.90? When the pH is exactly at 3.90, we'll have 50% of the Zwitter ion, the Zwitter ionic form, and then we'll have 50% of the form that has a net charge of -1. As we move away from 3.90 and increase to 4, 4.1, 4.2, 4.5, 5, as we increase the pH, what do you expect would happen with the population of these two? we would expect the -1 form of aspartic acid, that -1 charge, to dominate, and we would expect the zwitterionic form, its population, to diminish. All of that continues to happen until we hit a pH of what? Until we hit a pH of 9.90. At a pH of 9.90, let me see if I could maneuver this so that you guys could see. The alpha amino group comes off. So now we have this form, NH2, CH, CH2, COO minus, COO minus. We have the -2 net charge form of aspartic acid. And this proton starts to come off at around pH 9.90. So what happens when your pH is exactly at 9.90? You have 50% of the -1 form, and you have 50% of the -2 form. As we move away from pH 9.90 and go up in our pH to, let's say, pH 10, pH 10.1, pH 10.2, pH 10.3, pH 11, we would expect the population of the -1 form to diminish, eventually be removed, and the population of the -2 form, as we increase the pH, to increase. So that is essentially how you want to approach these problems. We've covered all the pKa's by going through all the pHs in which the protons will come off at their corresponding pKa's. But what is the pi? Okay, so the pi, if you remember by the definition, is where this form dominates, the zwitterionic form, in which the molecule of interest has a 0 charge, the form at which that dominates. Well, where does it dominate? Well, 50% of it dominates when you have a pH of 1.99, and 50% of it dominates when you have a pH of 3.90, remember? At 1.99, at that pH, you have 50% this and 50% zwitterion. At 3.90 pH, you have 50% zwitterion and 50% this form. So what is the isoelectric point? Well, it turns out the isoelectric point is where the pKa's are flanked. Okay? Or a better way to put it is where your pKa's flank to the left and to the right, where they flank your zwitterion. Here I'm using pKa and pH interchangeably. To do these types of problems, you want to get your pH value to match your pKa of that proton. That is when it begins to come off. And as you move farther and farther away in your pH, the population of the deprotonated form begins to increase for that ionizable proton. So the isoelectric point is nothing more than an average of where the zwitterion is flanked to the left and to the right. In this particular example, it would be 1.99 plus 3.90 divided by 2. That would be the isoelectric point for the amino acid aspartic acid. So doing that on my calculator, you will get a value of, essentially you can just do it in your head or do it in your calculator, but I'll just do it in my calculator. I got a value of, let me just do this one more time. I'm shuffling through multiple things here. I got a value of about 2.95. So the isoelectric point of aspartic acid is 2.95. So at pH of 2.95, that's very acidic. The zwitterion, the 0 neutral form of aspartic acid, will dominate. So this is how you want to do your isoelectric point problems. There is one amino acid that I'd like to talk to you about before we get into dipeptides and tripeptides, because for the examination you'll be given a tetrapeptide or maybe a pentapeptide, and you're going to have to figure out its isoelectric point. So this is a very simple example. But let's do one more example of one more amino acid before we move on to something more complicated in our next video. This would be the amino acid histidine. Can we calculate the isoelectric point of the amino acid histidine? Okay, that is our goal. Can we do it? Well, again, always consult your flashcards for the pKa's. That's going to be super important. If you don't have the pKa's on your flashcards, then essentially you can't solve the problem. So the PI of histidine. Okay, let's go through step by step. First thing, what do you have to do? You have to draw the fully protonated form of the structure, whether it's an amino acid, whether it's a dipeptide, tripeptide, or pentapeptide, whatever it is, you have to draw the fully protonated form of that molecule. So this is the fully protonated form of the amino acid histidine. Okay, a little bit complicated R group here, not my favorite R group. Be perfectly honest with you there in terms of being able to draw it so easily. It is called the imidazole side chain. Okay. So this is the amino acid histidine. Okay. What is the net charge of histidine here? It's +2. Okay, +2, +1 here, +1 here. So pKa values, consult your flashcards. pKa values do not get memorized. So the first pKa that comes out is going to be at a pKa of what? So looking at my notes, when you have a pH of 1.80, that matches the pKa of this proton. So at 1.80, this proton begins to come off, and you'll get this structure here. So 1.80 matches, the pKa of 1.80 matches this pH. So again, you have to imagine yourself just slowly raising the pH until it hits the magic pKa of those protons. All right, the next one, looking at my flashcards. Okay, don't forget to put your charges. What is the net charge of this molecule? It's +1. Are we at the Zwitterion stage? The answer is no. Okay, so what's the next proton that comes off? The next proton that comes off, according to my notes, is going to be at pH of 6.04. At a pH of 6.04, this proton begins to come off because it has a pKa of 6.04. So let's draw that structure. So I'm going to move this way. So draw along with me, for those of you watching online. This proton has now come off. And now we have a net charge of 0, a very important number because that's the Zwitterion. That's the Zwitterionic form that comes out when your pH hits 6.04, it begins to emerge. Remember, at a pH of 6.04, 50% of the molecules in the +1 state, 50% of the molecule is in the Zwitter ionic state. All right, so we're at the 0 form, the Zwitter ion form. What is next? Are there any other protons that could come off? Well, looking at your flashcards, we know that if we hit a pH of about 9.33, if we hit a pH of 9.33, we actually match the pKa of the alpha amino group, which is at 9.33. So this will start to come off at a pH of 9.33 because it matches that pKa of that amino proton at 9.33, and we'll start to get this structure here. So you can just draw this along with me for those of you that are online. And what do we have here? At pH 9.33, this proton begins to come off. When it's exactly at 9.33, we have 50% of the molecule in the Zwitter ion. We have 50% of the molecule in the -1 state. And now we have covered the full gamut of all the protons that come off in histidine. So let me just zoom out here. We start off with the +2 form. We go and hit the pH at 1.80 to knock off this proton. Then we amp up the pH to 6.04 to knock off this proton. And then we amp off the pH to 9.33 to knock off the alpha amino group. Okay? So as we increase the pH, we would expect the populations of these guys on the left to diminish, ultimately until we reach 9.33 pH and above, where the -1 form of histidine, its population will supersede all the other 3 forms and all the other charged forms of histidine. But what is the PI? Okay, the PI is where the Zwitter ion dominates. So the Zwitter ion is going to dominate here, where at 6.04 it's 50% Zwitter ion and 50% the guy on the left. At a pH of 9.33, the Zwitter ion will be 50% present and 50% the form or the guy on the right. So the Zwitter ion is going to dominate at an average of these 2 pHs. So the isoelectric point, as defined operationally, is the pH at which the Zwitter ion dominates. We will take an average of 6.04 plus 9.33, 6.04 plus 9.33 divided by 2, 7.69. So what is special about 7.69? Okay? What I'd like to submit to you is that this number is pretty close to physiologic pH, or as we define it, as pH that it would exist under cellular conditions, okay? Which, according to some textbooks, is 7.5, 7.6, 7.4, whatever it may be. This is very close to the pH that you would expect to find in the cell. So, having said that, we can actually say that histidine, by virtue of the fact that, if you remember our buffer conditions, the best buffer conditions are when pKa is ±1. Okay, when your pH is pKa ±1. So by virtue of the fact that histidine has an isoelectric point so close to the physiological pH of a typical cell, we can say that histidine actually has buffering capacity within the cell. Okay? So that's the overall point of why I wanted to go through the PI exercise for histidine, because if you have free histidine floating around in the cell, and if it's not part of any protein or what have you, it actually can buffer the cell and withstand large shifts in pH, both towards the acidic side and as well towards the basic side, because its pH or excuse me, its pI matches so closely to physiologic pH. Okay, so it has the best buffering capacity. So if you ever go to graduate school or work in a lab, many times in their experiments they do add some histidine, okay, because they want to mimic cellular conditions and keep the pH from going too low or too high. So that's something very interesting about the amino acid histidine, a natural amino acid that acts as a natural buffer within the cell. So if it's not part of proteins, in protein structure, many people outside of outside what's called in vitro in the lab will take histidine and put it in their solution so that it could be a best buffer solution. So those are how you solve PI problems. I want to talk about how do you solve PI problems for more complicated molecules, not just single sole amino acids. So we're going to talk about how to solve and obtain the PI for even more complicated species, such as dipeptides, tripeptides, and tetrapeptides in our next video.